Hello all. Having done with Unit 1, in today's session of parallel programming, we'll be moving on to the next topic of Unit 2, which is parallel programming on CPU. As of now, in Unit 1, I have just given you an overview of what is parallel processing actually, what are the benefits, what are the applications, and if you want to implement your parallelism, what kind of software models are required, what kind of hardware models are required. So directly jumping in onto the GPU for executing your program, first we'll try to understand how we can go for implementing parallel programming on a CPU. Now, here in today's session, we'll be going for two topics. One is your vectorization overview, the other is your hardware trends for vectorization. Before seeing what is vectorization, let me take an example here. Now I want to add two numbers R1 and R2 and store the result in R3. So what you'll write the instruction as R3 is equal to R1 plus R2. So each individual value will be summed up and stored. So each individual operation we call it as a scalar operation. Now if I want the same thing to be done in array, I'll just write it as A of I plus B of I and the result will be stored in C of I. And obviously, I need to go for using a for loop in order to perform this addition depending on the size of the array. Normally, if I go for normal scalar operations, what will be done? First, A of 0 value will be summed up with B of 0 value and the result will be stored in C of 0. And once this operation is done, then the I value will be incremented and then you perform on A of 1 plus B of 1 and this continues till the size of the array. But if I want to implement parallelism here, scalar operation will not be working. One after the other will not be working. So here we go for vector. So here vector is nothing but collection of values. Here I treat V1 as one array, V2 as one array, and there are some values in V1 and there are some values in V2 and all the values I want to perform only the addition operation and the result will be stored in V3. So for that we go for vectorization process where all the values of two different arrays will be summed up together and the result will be stored parallelly. For that, we have a hardware model which is known as vector unit. So you have a vector unit which is capable of performing single operation. It performs the same operation, I mean to say single operation on any operation plus minus multiplication or division but on different set of values so if I want to perform A of I minus B of I, instead of going for scalar operation, I'll just go for vector operation. Now we'll just see an example here. As we have taken the example of addition, A of I plus B of I. So in each clock cycle or one instruction, you perform one addition, store the result in C of I. Then you go for moving on to the next value. This is your normal operation. But when I go for using a vector here, all the values, assume this is 0, 1, 2, 3, 4, 5, 6, 7. So this is array A and this is array B. So all the values A of 0 plus B of 0 will be summed up and stored the result in C of 0. And simultaneously, you could see that A of 7 value is also getting added up with B of 7 and the result is getting stored in C of 7. They are not waiting for one another. All the operations are done parallelly. For that, we require an hardware unit. As I told you previously, it is nothing but a vector unit, which is capable of performing the same instruction on multiple data. That is the reason vectorization will use a process known as SIMD, which is one of the method of Flint's classification. So in this vectorization, you are to be clear with the terms vector lane. So what is vector lane here? Vector lane here is nothing but a path starting from your input till you reach your output. So this particular line, whatever you are drawing from input to your output, so this you call it as a vector lane. Next is your vector width. Vector width is nothing but vector. You just understand how many values you are able to add up simultaneously. Here, what is the size of your array? 0 to 7. 0 to 7 is 8. So the length of the vector here is 8. Coming to your vector width, length and width here are depending on each other. So if I go for vector length as 8, I mean to say 8 elements, and all these 8 elements are happens to be integer. So depending upon your bit processor, if I take integer takes 2 bytes of memory, then your vector width will be vector length into number of bytes occupied by each value. So 8 into 2 will be 16. So vector width is usually represented in bits. Length is a normal integer value. So 8 values, each value of 2 bytes of memory or 2 bytes of memory. So here it is 16 bytes. Sorry, it is 16 bytes of memory will be occupied. Now coming to your next one, instruction set. So vector instruction set is nothing but what are the operations I can perform. So you can go for add, subtraction, multiplication or else division on the set of values provided as input by two different arrays. Now when you want to actually go for implementing this vectorization, all these we are talking about on a single CPU. So you need to have a software or you need to even have a hardware. So you need to have a software and the corresponding hardware. So you write the instructions in a software, and whenever you're writing an instructions, you need to find a matching hardware so that you can execute this instruction onto the hardware. If you are not able to find the matching hardware, you go for a different hardware device which will make your instructions to work. Instructions alone will not work, right? You require a device which will make your instructions to work. So if there is a mismatch between the instructions written by you in the software and the hardware, you can go for a newer hardware in order to process these instructions. So for implementing your vectorization by using SIMD Flint's taxonomy, you need to find the corresponding software instructions as well as the hardware that is required to perform these operations. Now we'll move on to the next topic where we'll see what are the different hardware trends that are being developed from the starting in order to go for vectorization. And why am I going for vectorization to in order to implement parallel processing? So the first hardware unit that was developed by MMX and it doesn't have any full form, and this was focusing on a single precision values, and basically it was for the integer values. So if I want to perform operations, same operation on multiple values, single precision for integer values. Basically it was for integer values. Later on they have moved for a floating point with a single precision. Next, we have another technology where it is SSE, other hardware, which is streaming SIMD extension. Streaming SIMD extension. And this was the first Intel vector unit which was developed, and it was generally used for your floating point operations with a single precision. And later on, they have gone for SSE2 as it implies. The operation would be same. It was developed by Intel for floating point operations. The only thing is it was for double precision. These are all the hardware innovations that were made in order to support your vectorizations. AVX, it stands for Advanced Vector Extension. Initially, it was developed by AMD. It is Advanced Micro Devices. Advanced Micro Devices. Micro devices, and which was using a technology of FMA. FMA is nothing but fused multiply add. I'll tell you how it has been done. And later on, they have moved on AVX2 where it was developed by the Intel. The same thing where they have added the same fused multiply add operation. One was by AMD, the other was by Intel. And lastly, they have gone for AVX 512, Advanced Vector Extension 512. When you are seeing this 512, it is nothing but the number of bits of the precision they were using it while performing the floating point operations. And it was developed by both Intel and AMD. And they have Intel and AMD have developed various variants of this AVX. So these are the different hardware trends that are being used for vectorization. Let me first discuss about FMA here. So FMA here is nothing but assume I have an instruction where I want to multiply A into B plus C. Now here I don't have any FMA. So what you do, A plus normal operation A into B, then you add the A into B, you multiply, then whatever result you are getting, you sum up with C. So assume if it is taking 5 cycles for this multiplication, 3 cycles, overall it will take 8 cycles. But if we go for introducing FMA concept here, will not depend. So all the three inputs will be provided to this. This is a hardware unit, whatever we are calling it as an FMA, fused multiply add. And all these instructions are being provided. And both the multiplication operation and plus operation will be done simultaneously, and it would take only 5 cycles. So it tells you that the amount of time required for performing an operation would be reduced. Having seen the various features, so this is just a graphical representation of how the hardware units were evolved from 1997 to 2017. Initially, as we have seen, it was MMX, SSC, then they have gone for AVX, AVX2, and finally they have ended up with AVX 512. This is just a graphical representation to identify that different vector units were developed in order to maintain parallelism on a CPU. We'll move on to the next topic in the next class.